So the floor is yours.
Okay, so welcome everybody, and thanks for being here today. And I'd really like to thank Jan and Fabio for the invitation. I'm really happy to give this keynote this morning. So the presentation will be all about software composition from the point of view of scalability, because we usually use software composition and separation of concerns to make things scales. And then we're going to go through like different examples of what are the problem when you do software composition at scale, and also which kind of things you can do to scale the software composition paradigm itself. Just a few words about me before starting, so you know why I'm talking about this subject. I'm started my academic journey in 2007 when I was a PhD student in France, and since then I've worked in Norway, then back to France, and I've moved to Montreal in 2019, and eventually I became associate prof at McMaster in 2022. But all those different positions in very different contexts and apply to different things. In Norway, I was working on cloud things. In France, I was working on IoT projects. At UCAM, it was more working on agile things. All those different topics and work experience were really driven by the idea of emphasizing and pushing for software composition and separation concerns in very different topics and very different application domain. So that's basically the kind of things that we're going to go through today. And the first question, the first thing that you can ask if you are attending a PhD jury and you were not that attentive, and then it's your time for question and you don't have any question, the easiest question could be, does it scale? But what we're going to see today is that does it scale doesn't really mean anything. And actually it's a terrible question, because to really understand the notion of scaling, you have to be very clear on which dimension you're scaling. So that the kind of things that is really important when you consider something and you want it to scale. You need a baseline and you need like a target threshold, and this according to a given dimension. So first, I just went to the dictionary to look at the definition of scalability, and globally, the common acceptance of the term is the ability of something to grow, to increase, to upgrade on demand. So that's basically something which is related to the idea of growth. So let's go to the growth definition. And if we look at the growth definition, then the idea is the process of growing. Well, that was in the title, but it's more or less an evolution, increase, expansion in size. So the idea of scalability is to be able to grow in size and to expand the size of the kind of systems you're working on. Which brings us to the real question. Then the real question is not really does it scale, but what does size mean in your context? Because it's really, really complicated to define what size means. It can be line of code, it can be number of user, it can be number of server, it can be that a lot of dimension. And in the video that I've linked in the slide, there's a king of Norway who is competing with the USA, and eventually they conclude that they have the biggest alphabet. So because they have 3 additional letters than the US are not using, but they were less on all the others dimension. So that's really what we're going to go through today together, talking about size, talking about scalability, and how software composition works in this context. So first, I will go through an example of software composition applied to a cool project. Then we'll see out of 2 examples how we can work on software composition principle at scale, and we'll see that the scale is not always what we think. And finally, I'll conclude the talk by describing what it means to scale software composition instead of just working at a given scale, which is a slightly different problem. So first of all, composition in a nutshell. You're basically using software composition in your daily life, even if you're not clearly knowing it. So we are going to first look at an example and then generalize it a little bit. So the example I'm going to talk about today is this cool collaboration with the Geoscience Institute, where those guys, the PI of the project, his name is Gus Nollet. He was Princeton initially, and then he moved to France. And he's working on those huge buoy that each one is like 1.2 meters high. And they're basically putting the buoy on the on boats, and they're dropping the buoy in the Pacific Ocean. And they're using those stuff to support acoustic passive monitoring of the ocean. They're basically looking for earthquake, and they're listening to the earthquake waves, and then they're doing some geoscience with those things. So how does it work? Well, basically you have the buoy that is floating because you just drop it out of the boat. Then it goes below the surface, like 2,000 meters usually, and then it parks for up to a week or less if there's like a earthquake that requires you to go up to transmit data. And then eventually it will listen to what's happening, typically listening for earthquakes. And then we'll go up, we'll transmit the data through a satellite network, and then we'll go down. And eventually, that's really sad, but this is not energy neutral, so the buoy will die when it ran out of energy. So, well, that's a cool project. It's really fun to be on a boat and drop stuff into the ocean. But we were talking about software composition and scale, so that's kind of a weird example. And actually, so Gust, the PI of the project, knocked at the computer science lab door, and he was like, okay, I think I have a problem with my mermaids because the ocean is full of challenges. I mean, I'm listening to earthquakes, but there's other scientists that wants to do other things with those kind of buoy. You can listen to earthquake, but you can also listen to whales to follow the whales population because it's an endangered species. You can follow plastic pollution. You can monitor the water temperature to check climate change. You can monitor the concentration in salt in the water to get information about how the different body of water are moving into the ocean. So basically his point was like, I have an iPhone, and on my iPhone I have apps that basically I can run any app I want on the iPhone. So can you build an app store for the mermaids? That was how he concluded his first introductory email. And there was a lot of problem there because the mermaid, it's clearly not a smartphone. It's very old legacy Haddock code. There's not even an operating system on the stuff. It's really close to the metal, and it's deployed in hostile environment. There's salt, there's pressure. It's really energy dependent. So there's a lot of cares that needs to be done into this. And his point was really about composing data collection campaign. Like the scale was, I have several people who want to use one single mermaid, and how can I compose their needs, compose what they want to do inside the mermaid so that it can monitor the whales and monitor the earthquake at the very same time. So this is an example of the kind of things we've done in this context. That was a PhD of Sébastien Mossel in 2020. You have for example, the marine biologists that express how to monitor whales, and you have the geoscientists that express how to monitor earthquakes. And then we're going to merge both applications so that the first composition, and here the scale issue is being able to handle very different needs from the biologist and the geoscientist, and also being able to identify conflicts that might be related to energy consumption. If when the biologist and the geoscientist code require the mermaid to go up every single day, then it would be a huge problem in terms of energy consumption because it would ruin the battery. So that was the kind of conflict that we had to detect by simulation and stuff like this. And then when we obtained the right composition of data collection campaign, the point was then to compose this application with the platform model, which was the MERMAID buoy, and then obtain the running code that was then checked and deployed by the hardware engineers on the MERMAID. So When I will be talking about software composition in this talk, that's the kind of things that I'm going to refer to, like this idea of having separated concerns and having like a way to compose them and enact them into action in the project. And actually, you're using software composition even without knowing it, because each time you modularize code, each time you configure a kernel, each time you pull code from a Git repository, well, basically, you're using a software composition mechanism. When you're doing a Git pull, you're composing the code from another branch with the code from your branch. When you're configuring the Linux kernel, you're basically composing a set of different features, a set of different drivers into one single kernel that will be deployed in your computer. So that's really important to take into account that software composition is actually everywhere. And each time you want to tame complexity, usually you divide, and the point is to divide to conquer. So you have this set of separated stuff, but eventually you have to compose them back together to be able to then obtain the running system. Which leads us to the second part of the talk, which is now that we know that, okay, there's composition is banal and that we're all using composition in our daily life. Why do we have a scaling issue? I mean, if it's already working, so where the problem? Well, first, the idea here and the point is that, as I was saying at the beginning, if you want something to scale, you have to define the dimension that you want it to scale and the kind of size you're going to measure. For example, at the beginning of the 2000s years, there was a huge hype about aspect-oriented programming, because aspect-oriented programming was all about solving the separation of concerns problem. The point was to automate the weaving process and find that you can express all your concerns as orthogonal separated aspects, and then the weaving will integrate all those aspects, all those concerns together to create the final application. And if you look at this in terms of engineering, programming language, and design, the aspect J, which was the reference implementation of AOP in the Java context, it's an engineering jewel. I mean, that's amazing. The way the bytecode is processed and the way it's integrated, the way the weaving works, the point cut works, that's just amazing. But the main issue was that this is not what needed to scale, because the integration was a huge problem, and this is clearly solved. But the real thing that did not scale, according to this approach, was the design of really independent aspects in the system, and the fact that those concerns were conflicting with each other and would then generate weird behavior. So that's really an example of something that is really solving a very, very important problem, but also missed something, which was a scalability issue. We can look at something more concrete, like the Linux kernel. If you look at the modern version of Linux, you have 1,500 feeders. So it means that in the worst case, of course, there's dependency between those feeders, but the worst case would be 10 to the power of 452 different combination of those feeders, which is an interesting number. It's a number that is even too large for Python to print. And if you consider the number of atoms in the visible universe, it's 10 by the power of 80. So according to Jean-Marc Ezekiel, if you're an astrophysicist, you're dealing with objects way simpler than what we are dealing with in software engineering. So that's the kind of scalability issue we are considering. 150 stuff, it's not that big, actually. But if you take it from a software engineering point of view and consider like those things as the main points of interest, then you might have an issue. So we can look at an example of Linux engineering at scale, which is also quite impressive, which is Coccinelle from Julia Lawal and Gilles Muller in France. The idea of Coccinelle is to support rewriting rules. So when you're working into the Linux kernel, there are some guidelines that you have to follow because, well, you're basically coding the kernel. So there are some stuff that you need to do and some stuff that you're totally forbidden to do. And there are some mistakes that can be fixed automatically. So what they've done was basically they provided a set of rewriting rules. There's up to 59, and there are 35 rules that are run automatically when you commit. That basically rewrites the program to fix the problem. So it's a transformation from program to program, and by definition, those rules are composable because you can just apply them in sequence, and that's basically function composition. The size here is a problem, and that's kind of a regular size we're used to in software engineering. Lines of code. Linux is 20 million lines of code, and there's 7,000 commits per month in average. So basically, each time someone commits, then you have to rewrite automatically 20 million lines of code, which is kind of a big deal in a way. Here is an example of what Coccinelle is doing. On the right, up there under the penguin, you have a program which is basically allocating memory. That's a kmalloc, kernel memory allocation, and then setting the memory, memset, to 0. And this is like a violation of good practices in Linux, because you should not do that. You should use one single instruction to do that, which is kzalloc, kernel 0 allocation. So to fix the problem and ensure that this situation never happened in the kernel, the Coccinelle rule, which is bottom left of the slide, is all about that. The lines that start with a minus are the lines that you want to match and you want to remove, and the lines starting with a plus are the lines you want to add. So these rewriting rules basically said each time you find a kmalloc followed by a memset, then you're going to remove those two lines and you're going to produce one single line, which is the kernel 0 allocation. And then the programs, the P prime is okay with the guidelines, and then you can go through. And then, based on this, they applied separation of concerns. So they have all the different good practices in different rules, and they apply the rules on the kernel each time you commit and you run the make cocci-check instruction. And it works like a charm, actually. It works like, it takes 3 hours, about 3 hours to rewrite 20 million lines of code on one laptop. That's just totally okay. It triggered 35 rules that are applied in sequence. And this is, I mean, we're talking about graph pattern matching. So that's really impressive, the fact that it's scaled under the 3-hour threshold. But the main problem here is not really the application of the rules, it's the way the different rules are composed with each other, because Coccinelle doesn't look for fixed points or conflict detection or things like that. Their point is like, we have the rules are correct, we're applying the rules, and it works. And typically, there is no guarantee that the rules commute. So you've used one order, but maybe if you had used another order of application, then you would have ended with a different version of the kernel. That would be a problem. And if you take the number of combination of 59 rules, then it's the scale of the order of magnitude is the number of atoms in the visible universe. So that's kind of big. So that's the kind of things where software composition need to scale and needs to be like considered as a first-class citizen in the process and not a bypass product. So what we've done in this context was to define a new operator that was part of Benjamin Benny's PhD in 2019. And we had two objectives: find a way to identify conflicts, like situation where the rules were not commuting and that would result into a weird version of the kernel code. And also we wanted to stay in the 3 hours windows, because then it doesn't make any sense to explode the time, because you have to run this stuff 7,000 times a month. And eventually, so I'm not going to dig into the details, but we ended up with a new composition operator that was slightly different from classical function composition. And with this, we validated it on a 19 version of Linux. Actually, it was surprisingly slightly quicker than the sequential function composition. And also, we were able to identify two rules that were conflicting. And that's something related to scale too. Before, you had to work on the combination of 59 rules, which is impossible at human scale. But now you just have to focus on two rules that sometimes conflict on some version of Linux. And then you can clearly look at those two rules out of 59 and check what's happening. I will go to another project, totally different, but that's the same kind of software composition issues that you can find. If working on the Linux kernels drives you mad, well, eventually we have the Relay project in the team, which is all about mental health. And mental health is a huge issue in Canada for various reasons, but the geography of the country is part of it. In fact, it's a very, very big country with complicated access to healthcare, and especially mental health. And in this project, which is a New Frontier in Research project, we have two objectives. One objective is to collect textual conversation from patients, that people going to the psychiatric ER in Switzerland and Belgium, where our partners are. And we're going to, after collecting their consent, we're going to absorb all the text and message they have on their phone. Text message, WhatsApp, Messenger, Twitter, all those kind of things will be fed to a natural language processing model that will be used to support suicidal risk detection. So that's the very idea of the Relay project. So this is basically how it works. We have the patient on the top left that came with all of his or her message received at the ER because going through real mental health problems. And then we collect consent, the patient accept, and then we collect the messages. Those messages are anonymized and given to an NLP researcher that do their magic to build a real predictive model. And then any other user can install the app on his or her phone and use this to get like feedback on what they're writing, and the app can kind of tell people like, you don't really look good those days, maybe you should talk to someone. That the idea is. It's a support. It's not a diagnosis application, it's really providing support to people. And then you can say, okay, where's the scale issue and where the separation of concern issues here? It can be the number of apps that you have to absorb, the number of patients that you want to do, the complexity of the data to feed the predictive model. Well, actually, the main issue is the number of countries, and it was only 3, but that was a huge problem, because if you're starting to say that you're going to collect text messages, very personal information, very private information from people that has maybe tried to commit suicide or stuff like this, I mean, it's clear that you have to go through an ethic board and you have to convince and be convinced that you're not doing wrong with the data. And I mean, we're talking about research involving human participants in very, very particular situations. So we have to be crystal clear about what we're doing. And this needs to be done in Canada, in Switzerland, and in Belgium, because, well, the patients are in Europe and the data are handled in Canada. So basically, our scaling issue here is not the number of patients, not the number of apps, not the cloud deployment, all those kind of things were kind of easy. We know how to deal with that in software engineering. The point here and the scale issue was to convince the ethics committee and convince ourselves that what we're doing was the right thing to do. And it's super long and it's super tedious, and it took like 15 days before COVID, and we'll have to do it again after COVID because rules changed. That's really, I mean, this is necessary considering the context of the project, of course, but this is really tedious project. So here, the scaling issue is finding a way to, in a way, model what the justification for the ethics board, and then find a way to project this into what is required for Belgium, what is required for Switzerland, what is required for Canada, and those kind of things, in a way to strengthen the data management plan that you can encounter and give confidence that you can defend it, because you're really working with the health of people in a way. So you have to be really convinced that you're not doing wrong. And the ultimate goal here is to provide a support to developers by having a way that in your IDE, for example, you're working on data and you want to store the data, which is like, okay. But if you compose this with the concern that comes from the country and the ethics approval that you had, it gives you additional way of using the code. Like in this case, you can't save something in the database if it wasn't anonymized before, because then we'd be able to find the patient back in the database. So this is something that we're working on. And for French-speaking people, we had a 1-hour discussion with ElectroMonkey podcast all about data and like private data, and from a software engineering and NLP point of view. We're not privacy engineer, but the point was really to identify the interface with privacy problems and what you can do from software engineering and AI point of view based on this. So it leads us to the second conclusions of the talk. Like, scaling is not always about big numbers, actually. 3 countries, not that big, but months of work to make it scale. In the Linux kernel rewriting, 59 rules, not that much, actually. It's 59 files, but then huge problems if you try to combine all the things together. So that's really something that needs to be kept into consideration. Like when we're talking about scales, we imagine millions of users, thousands of servers. Well, it's not always like that, actually. Which brings me to the last part of the talk, which is scaling composition and considering composition as an application domain by itself. As we've seen, legacy, there's a lot of legacy composition operator. Each time you're using a Git merge, you're basically using a software composition mechanism. And in the case of Git, it's more or less close to one function of 4,000 lines of very, let's say, heavy C code that is triggered to support the merge. And we've worked with Mathieu Hacher, who is a designer of a project named Familiar, which is also a composition operator in the context of software product line, which can be considered as legacy. I mean, it's close to 15 years old now. It's 241,000 lines of code, and it's kind of like a heavy code too. So it's kind of a complicated application domain. And when Mathieu is using the merge operator that is defined in Familiar as a way to build a software product line, the merge is commutative. Like, you can merge in any order, it will produce the same result. But if the first argument is bigger than the second one, then the time becomes totally insane. And that's because of some internal stuff that are done at the implementation level. So what we tried to do in this context was find a way to work on the composition operator as black boxes and identify properties. And if we can clearly ensure that the merge is commutative, then we can save hours of computation. The point is not to fix Familiar, because you don't want to touch those 200,000 lines of code. The point is really to understand how it works and then find a way from an engineering point of view about how to integrate it. So what we've defined, that's ECMFA GOT paper in 2020, was a way to do some property-based testing. So we had a way to, we created a DSL to express properties of operators, like this operator is associative, this operator is transitive, and those are the assertions that would check it. And then we're able to define the operator modeling, like this operator should be associative based on the equivalence, and this operator should be commutative with the equivalence relation. And then we're using property-based testing approach to empirically check that those properties were true. And then based on this checking, we're able to enact it in the code to use this. So we clearly have to take into account the fact that there's a history here, there's a legacy we have tons of composition operators that do exist in the wild, and when we're working with them, at some point, we need to consider them as the object of study and not just a byproduct used to eventually recompose all the things together. Another dimension in terms of scaling the software composition paradigm is really to stop reinventing the wheel. Each time you move to a new application domain, then you might have to write a new composition, or you have to adapt a composition system, or to project into a composition system that is already existing. And well, if we go back to the Linux rewriting, for example, we applied it to Coccinelle, and that worked super well. But there's also a lot of other rewriting systems that works. We worked with Spoon, which is a Java-based rewriting system, to rewrite some Android application and fix energy efficiency and anti-patterns in the code. And we also use some rewriting of Docker deployment descriptors that were not following good practices. So the formal model of the operators that was defined in Ben's PhD is the very same. It's just like it was projected into different application domain to be able to scale those different applications. And that the real point, we need to really, by considering the software composition operators as something worth studying by itself, we can have a real and nice formal model that can be then applied to very different application domains. So I will not dig into the detail here, but the real point here is really to identify when we're working on something, what is domain specific, what is composition specific, what comes from the composition paradigm itself, and then how can we define things in a reusable way. For example, in 2018, we used the very same formal model that was projected into two different application domains, two totally different domain. One was Docker, and the second one was many world graph databases, and the abstractions were the same. It was about merging and reconciliating stuff, but the devil's in the details, and the application to each domain is still a contribution by itself. But by having one single formal model that we already knew that was good, then it was easy to focus on how to do it right in each application domain instead of addressing how to do it right, plus how to compose at the very same time. And this is my last example of scaling issue. So this is something which is very recent because it was accepted like 3 weeks ago or something. We're working on agile user stories. So as someone, I want to do something so that blah, blah, blah. And there's a reference data set, which is 1,600 stories and representing 22 products. And then what we wanted to do was to identify similarities between the products. And actually, if you do that, then you obtain something which is 4 million stuff, which is 122 CPU hours. So what we really needed in this case was, from the beginning, a way to compose our stories and user stories together into a coherent and consistent backlog needed to scale from the beginning. So what we've done was to first try to escape from the classical Java ecosystem that those research were done, and we teamed up with people who knew how to work with large graphs, like a bioinformatics colleague. We tried some graph database, it did not scale, so we went to his technology, which is Python NetworkX, and we used some NLP development expertise. And the point is really like, we needed to adapt and find the right technology to support this. So the fact that the operator needed to scale led us to the wonderful world of Python. And actually now it scales, and we are able to work on this level of composition in this case. Which leads me to the final intermediate conclusion, which is that composition is an application domain by itself, and that you really have, if you want this thing to work in a way, considering it is very important. Like, software composition is not just a byproduct of what we're doing as software engineer. That leads us to my conclusions. So software composition is everywhere. We're using it to solve the programming scalability in a way, divide and conquer, like tame into small concerns and then compose back the concerns together. But it requires expertise to clearly scale. So what we can do as software engineer is really counter this, re-hi-fi those operators, and also re-hi-fi what scales mean in our context, because the does it scale question still doesn't make any sense if you're not defining the kind of scale and what are the elements, what are the size you're measuring. That is important. Of course, the work I've presented today is a team effort. Those are the graduate students that contributed to the different projects that I've showed today. So thanks to them, because without them, this work would not exist. And I will conclude by some blatant advertisements. At McMaster, we are really looking for a postdoctoral, PhD, master, summer internship, We have also faculty positions that are opening from next year. So there's a long-lasting tradition of industrial collaboration in the lab with some very exciting industrial projects. Like we starting one project about safety over the air, software updates, change impact, safety insurance, tooling, automation. We have tons of opportunity in terms of recruitment. So if you're interested into joining us at Mac, feel free to send a message on the Discord or contact Dr. Pentelik, who is in charge of the recruitment. And that will be all for me. And I was always 4 minutes late. Thank you very much.
Thank you very much. I hope you can hear the claps.
I hear the beginning of the claps. So it was a very brief one.
Okay, well, I think we'll start with questions from the audience here, and then we'll go through Zoom, okay? So has anyone a question or comments on Sebastian's presentation? Ooh, so silent, all of a sudden. No? No question, no comments? Well, actually, I have a question, Sébastien. So you show us many examples of scalability, but then do you think it's hopeless, actually, to have like a general solution to the problem? Is it really like a problem that we have to address each and every time again and again and again?
I think a generic solution, like a framework that would solve any composition scalability issue from the beginning, is kind of a hopeless quest, because there's really a lot of devils in the details in a lot of different application domain. But what we really do need is a way, like a catalog of the different good practices and good solution to fix all the different scalability issues that one can encounter. And then we can reuse and reapply those. It can be an abstract algorithm. It can be like a graph composition library. It can be like a lot of different things that needs to be adapted to fit in the domain. And this adaptation is clearly a problem in itself, but we really do need those catalog of composition good practices, instead of just like, okay, my main focus is about separation, and separating is super important, of course. But then if we are not thinking and reifying the way we compose back things back together, then we're just like missing half of the problem in a way.
We need patterns, basically.
Kind of.
Great, thank you so much. I see Bram has his hand. Bram, please go ahead.
Sure, great talk. Thanks for that. So I've also worked in the past a bit on AOP, and I share your sentiment you had when you talked about that. But I was wondering if you would, with your knowledge now, also with the work you do on composition operators and so on, if you would have been there at the start of AOP, would you be able to change something or something to make it work and scale?
Yeah, the main issue with AOP, actually, and what happened with the aspect, the design of aspect, it's so complicated to clearly design an aspect that is going to be composable with others. So it means that I'm not sure they've done anything wrong in AOP, actually, because that's really it's working quite impressively, but it's just like it can't be used to solve any problem. It works super well on very dedicated problems like database persistence. That's awesome. Logging, it's also awesome. Security, you have some good application of AOP in security that works pretty well. But since you're starting to talk about business features and having a way like having this utopia of I have a catalog of any features that are going to be composed together to create application on demand, this was like not the right quest. So I'm not sure anyone could have been change anything or change any paths on this, but it's more like it was kind of oversold actually in like this express everything as aspects and everything will work. That just doesn't work. Find the right aspect and use aspect-oriented programming to integrate this. That's just awesome. If you're using Spring, the classical Java stuff to deploy microservices those days, there's a huge use of aspect-oriented programming inside Spring, and it's heavily used inside Spring, so it works at scale in industrial context, but it's hidden, and people are not exploiting the aspects, and the aspects are composed, and they were carefully curated to be sure that they're composable together. So yeah, that's I'm not sure you can change the past because it had to happen in a way, and that's also led to different kind of like addressing the composition problem differently, because now we know in a way that this can't be done in this way.
Yeah, I guess it's a learning experience in that sense. So that's great. Great, thank you.
Thanks, Bram.
Thank you. Any other questions by Zoom or by in person? Anyone?
Yeah, maybe.
Oh yes, there is a question by Rizlan.
Okay.
I mean, you cannot see her, but she's.
Hi, Rizlan.
Hello, how are you? I missed the beginning of your talk, so maybe my question is obsolete. You already answered the question. So from Jan's question, I'm wondering if composition should be refined as a concept, because most of aspect-oriented programming was focused on, let's say, transversal aspects that you can compose, versus when you compose services or you compose, I don't know, you want to release different systems that you already or components and you want to compose them. So at different levels, the composition should be maybe regarded in a different way, and you define depending on what is it, a transversal function, or is it a business-oriented function, or other kind of I don't know, service. So I'm not sure maybe you already discussed that in your presentation. So I'm wondering should we redefine the concept itself?
Yeah, I think the idea of software composition should be considered as an application domain by itself. It's often considered as something which is orthogonal to what you're doing, and then you're separating, and eventually you compose. And then when you have all those stuff together, you're like, oh shit, I have to compose them back together. So for sure, it needs to be addressed as is. And based on your question, like it can't be. It can't be like a black box that would compose anything. The point is really to reuse, to transfer, like back to the AOP example you were giving. Aspect-J works super well, but there's no way I can reuse the way they're detecting conflict in another context than the one that Aspect-J used. Or there's no way I can use the rewriting and the aspect integration in a way that is different than the way they were using it. So they were implementing it. So that's something that maybe we should work on and address in identifying things that are modules where we're composing. We're always trying to find a way to separate, find a way to identify conflicts, find a way to integrate things together. This can be weaving, this can be merging, this can be done at the model level, at the code level, at the bytecode level. There's tons of different way of doing this according to the application domain. And by expressing a catalog of, Jan was talking about patterns, it can be patterns, it can be a reusable library, it can be stuff like this, but for each of those different dimension, then we might be able to support it. So the study would be the family of software composition mechanism by itself that could be an object of study, and this is not a transversal thing. It can be considered as a domain by itself. I'm not sure if I'm answering your question.
Yeah, somehow you did.
Okay.
Yeah, I was wondering if we can have a catalog and separate weaving things inside the code from the real composition, because the way I see it, aspects. Yeah, it's a composition that is a bit. It's not like a mathematical composition. To raise inside, put an aspect inside something that exists is very different from the composition concept. I'm not sure if it makes sense for anyone.
Maybe only because we don't have immutable language.
Yes. Yeah.
Also.
Yes. Yeah.
But if everything was immutable, like the previous,
yeah.
then it would be better.
Exactly.
Yep.
Yeah.
And easier, no, not better, easier.
And actually, there's amazing composition mechanism inside Lisp, like what were available in Silos and stuff like this. That's just awesome. And then it disappeared because then the hype went to Java and things like this. But that's there's a lot of lessons to learn of the way it was implemented in Lisp and all the meta programming that is available in Silos. It's also Joule.
Any other questions? By Zoom, anyone?
So just Jan, one point is if people would like to do questions by Discord, we are monitoring and we can reproduce. So also thank you, Sébastien, for your talk. I wondering about the questions about ethics. For me, you discuss super well the problem, not the problem, but how hard is to conduct some experiments or research in this domain about health and mental health. Maybe for you, what's the most challenging task or problem that you did during your experiments and your research on mental health?
I think the main issue that we had was to convince ourselves that we were not doing harm or wrong thing. Because it's really like, I mean, when I was working on the MERMAID, the buoy, that was super fun to throw buoy out of the boats, but then no one could die, except if falling out of the boat, but that it's not because of me. And then when you start talking about mental health of people and gathering very private information, like gathering the messages of someone who just tried to commit suicide, then it starts to become a total different burden in the way you're applying and in the way you're, like, your code. I mean, as software engineer, our code matters, of course, but in this case, it's even worse because you're working on data from people that are really, really like in a bad shape. So convincing yourself that you're not doing wrong, writing it to an ethics plan, because usually from software engineer, the ethics board, it's seen as a burden. Like, oh, I have to interview people and they ask me for an ethics certification, but I'm just doing a survey, so that doesn't make sense. In this case, I mean, it's totally different because then you really need to be careful about what you're doing. And it's also kind of a relief that someone else, like a board, looked at what you want to do and said that, okay, you can do that. That makes sense to do it the way you want to do it. But then the burden is when you have the interns, when you have the students, when you have the developers that worked on the code, it's your responsibility to ensure that those ethics certifications are respected in the code. Because, well, you claim that you're doing it, so you can't not do it in a way. And that's one of the main problem that we're encountering. Like, be sure that what we're doing in the code makes sense with respect to what we told that we were going to do.
Perfect. Thank you so much.
Thank you. There is one question.
My question may have overlap with the first question. So, how general the different compositions are like across different languages, different domains, different applications, or how specific?
If you look, for example, at the parallel operator that we've defined in the context of Linux rewriting, the operator by itself, it's kind of just shifting the paradigm. Instead of applying function in sequence, we were just basically applying them in parallel and checking things, working on the diff instead of working on the function. That was the main breakthrough in this. And then we're able to apply it to Docker, apply it to Android, and apply it to Linux, like those IDs. So the abstraction and the ID, the paradigm by itself is totally reusable. It's just like, instead of focusing on the function, focus on the diff produced by the output. But then implementing it in the context of Docker, the context of Spoon for Android, or the context of Coccinelle for Linux, that requires a huge effort. And each time the let's say the validation experiments had to be different, and those were different empirical results in a way. But the fact that we knew that the composition operator, the parallel operator defined by Ben in his PhD, was able to solve the composition problem, we were able to solve the scaling issue in a way by applying it to the thing. So that's where we need to find the threshold, identify the abstractions that are reusable enough to be reused in different contexts.
Thank you very much. Thank you, Sébastien, again for your talk. It was great to hear and great to see you. We're gonna stop here and then go to the next presenter. Sorry. So thank you again.
Thank you, and really thank you for the invitation. That I really liked that.
Thank you so much.
Okay, so the next presentation is